Okay, so today's lecture is about kind of a review of probability, and more specifically, the problem, what's called probability density estimation. And again, if you took a probability course, which you all should have being in this class, the first 20 minutes of this hopefully will be like super review. If anything I say in the first 20 minutes is like, what is he talking about? Then I think you have to kind of step back and think about, okay, do I have enough probability background to be able to understand the rest of this class, right? So, the key concept of probability is what's called a PDF, probability density function, right? So the key idea is a PDF, which stands for probability density function. And when you first learn about probability, you also probably learn what was called a probability mass function, PMF. And the difference between these two things is whether your random variable is discrete or continuous, right? So for example, if I roll a die and I get one of the 6 outcomes, 1 through 6, then I have a discrete sample space, right? Which means that I have a PMF that looks like, outcomes on this axis, the probability on this axis, and then you can think about this like kind of a bar graph, right? Of, over all the possible outcomes, what are my probabilities of each outcome? And all those numbers should add up to 1, right? Because there's one total amount of probability in the sample space, right? Now, when I taught probability, I like to draw this with delta functions, little arrows instead of bar graphs, right? Because that makes a closer tie to the PDF idea. I'm not going to be so picky about that, and I'm not going to really draw a lot of bar graphs here anyway. But basically, this is like the discrete world, right? So this basically, sums to 1. And then so basically these bars here, the bars sum to 1. And then if your sample space is continuous, say, you wake up and you take a measurement of the temperature, right? That's a real number, could be anything, right? Anything on the real axis. Instead, I have what's called a PDF, right? Probability density function, where again, I have outcomes on this axis, and then I have, the PDF on this axis, and this function integrates to 1. Right? So this is basically, a PMF is actually like a special case of a PDF, and that's sometimes why, for you mathematical people, that I draw out like delta functions, because then the idea is that those delta functions are actually accumulating probability as I integrate across them, right? So then I could say that, in general, a PDF is a function that is always positive that integrates to 1, right? Or non-negative that integrates to 1, right? A common mistake is that in the continuous world, this, you might think of, so kind of here, colloquially, you think about this as the probability of getting outcome X, right? That's not the case in continuous world, right? That's one of the first things that we try to kind of drill into you is that, the value on this axis is not itself a probability, right? Because, for example, let's think about, something like this, where I have a uniform distribution on the range 3 and 3.5. So this is a valid PDF, right? It basically says that, how do I compute probabilities? It's like saying, suppose I want to know what's the probability that I am between 3 and 3.25. What I do is I integrate the PDF in the range that I care about. That's called an event, right? And so what is the area of this box? Well, it's 1/4 unit wide times 2 units tall is a half. And so I can say the probability of being in the left-hand side of the box is a half, in the same way the probability of being on the right side of the box is a half. But it's not like I can say, what's the probability of being, 3.75? It's not like you can read that off the graph and say, oh, the probability of 3.75 is 2, right? That doesn't make any sense because I know probabilities have to be less than 1, right? The only thing I could talk about with a PDF is integrating an area, right? So it should not be hard to convince yourself that the smaller that area gets, the closer I get to 0, right? The thinner that box in red were to get, the more I would get to having 0 probability under the PDF, right? So except in rare circumstances, the probability of getting any actual number value is 0, right? I can only talk about being within plus or minus of that number value, and that's some sort of positive number, right? So yes, so basically we integrate areas under the PDF to get probabilities. That's the way you should look at a PDF, okay? And in a more general sense, this is harder to draw, but if I have like a 2-dimensional PDF, like in XY, and I want to know, so if I were to draw that in XY, that's going to be some sort of a, function. I'm not great at drawing in 3D, some sort of mountains in 3D over the XY plane. And again, if I integrate over all of X and Y, I should get 1, right? And then if I want to know what's the probability of being inside this area, what I do is I say the probability of A is the integral. In this case, it would be like a double integral of A over the joint PDF of X and Y, dx dy, right? Sometimes when we're talking about multiple dimensions, I'm not going to be specific about how many d somethings I need. I can also just kind of say in general, the probability of event is the integral over that event like this, where this could be, multiple dimensions. Okay? So that's kind of like the mechanics of how do I, work with a PDF, okay? Then we kind of talked about these kind of ideas of measuring properties of a PDF with these things called moments, right? So the first thing that you learned is expected value and variance, right? So there's this idea of the mean of a distribution, right? Mu, often we call it. So if I have a random variable x, I would say that this is the same thing as the expected value of x. How do I compute the expected value of x? I take the function x and I integrate it times the PDF dx, right? In general, the expected value of some function is the same thing. Maybe make this clear, this is an f, right? That's like saying I integrate the function of x times the PDF of x dx, right? That gives me kind of like the mean value of that function according to the probability distribution of the data, right? And the same way, we talk about the variance of a distribution, sigma squared, or the variance of x, as the integral of this function. Right? The variance is kind of like a measure of the spread of the data, right? So small variance means that the PDF is really peaked around the mean very sharply. High variance means it's spread out more, right? And this generalizes to multiple dimensions, right? So I could do this in whatever number of dimensions I wanted to, right? Instead of having a variance, I would have what's called a covariance matrix. We'll talk about that in a second, okay? Okay, so that's the basic idea. And so in general, a PDF is any function that is non-negative and sums to 1, right? I can just kind of draw something that will work. But in practice, we like to use these kind of like named probability distributions that are controlled by a small number of parameters, right? So normally I'm not writing out the function of the PDF as some sort of complicated polynomial or Fourier series. I'm just writing it like a Gaussian or an exponential function. We give names to certain special distributions that turn out to crop up all the time in engineering and science and machine learning, right? And so that's generally what we call parametrizing the distribution, okay? So often in machine learning, we are trying to fit a PDF to data. And that's really what today's lecture is all about, right? And so we're going to talk about doing that in two ways today. One is what's called parametric density estimation, and the other is called non-parametric density estimation. And so the easiest way to do it is what's called, parametrizing the PDF. For example, I choose a known family controlled by a few variables or a few numbers, a few, knobs. Right? So it's kind of like I'm trying to tune this thing to fit, right? So the parameters we might call theta. And what we're trying to do is to try to find the best theta that fits what we see in a given data set, right? And so the most common PDF, the one that we use all the time, is called the Gaussian. So, very common PDF is called the Gaussian or normal distribution. Okay, and what's the PDF? This is just in one dimension, 1 over square root 2 pi sigma, e to the minus 1/2 x minus mu squared over sigma squared. Right, so this is your old friend, the bell curve, where it looks like a symmetric distribution around the mean mu. The smaller sigma is, the tighter the peak is, and the bigger sigma is, the wider the spread is, right? And so here, if I'm thinking about this as a parameter estimation problem, my theta that controls the distribution consists of mu and sigma, right? If I tell you those two numbers, I've told you this whole function, right? And in higher dimensions, we need to have more numbers, right? So in higher dimensions, the Gaussian PDF looks like this. Again, here, my x now is a vector, right? So I'm kind of overloading what x means. If I have like d dimensions, then this is my Gaussian. So here, this sigma now is basically a d by d, what's called the covariance matrix, which is symmetric and what's called positive definite. And here I'm taking the, just in case you don't remember what these symbols mean, this is the determinant, this is the inverse, this is the transpose, and so now this and this mu here is basically a d by 1 vector. So now I have to have d numbers for the mean, and I need to have like, kind of like 1/2 d squared or something like that of the, covariance matrix parameters, right? It's not fully d squared because the matrix is symmetric, so it's like, whatever, d times d minus 1 over 2, something like that, right? But on the order of squares. And so, and just kind of like thinking forward, you can imagine that, this is a lot of knobs to turn to figure out all these numbers, right? So just like we talked about last time, we need to have enough data to be able to fit all these numbers, right? So if I gave you just like 2 data points, you wouldn't be able to estimate a multidimensional Gaussian because you wouldn't have enough degrees of freedom, right? And in the same way, even though no one can possibly imagine it this way in their head, like one of these massive billion parameter transformer networks is also just like, in a way, a crazily parametrized function, right? One that no one could possibly write down or understand, but it's like you're turning all these knobs trying to fit this function to your data, right? So the goal in general is to fit so suppose I give you some data and I say, okay, I want you to fit me the mu and the sigma, assuming this is a Gaussian distribution, right? I want you to find the best mu and sigma. What do we mean by best, right? So usually when we say the best fit, we're talking about what's called maximum likelihood estimation, okay? So you know, we often want to fit the best PDF parameters to some data. Okay? And so let's think about how that would work, basically. So kind of what we typically want to do is what's called maximum likelihood estimation. Okay? So typically, we use what's called maximum likelihood estimation. Okay. And so let's suppose that we have a bunch of observations we're trying to fit these Gaussian parameters. Okay. So e.g., let's say we're doing a d-dimensional Gaussian. So the setup usually is that I have my observations, my data points, and I am typically assuming that those data points are what's called, bam, IID. Okay, so we have IID observations, x1, say, through x. Let's see what will be. What's the right way to do this going forward? Looking at my data here. Let's just say n. Right. So what this stands for is identically and independently distributed. Right? We assume that all these data points are coming from the same underlying Gaussian and that there's no statistical connection between sample 1 and sample 2 or sample 3, right? If we did have dependent samples, then life would probably be pretty complicated, right? So one example of like when that's not the case is something like, say you're taking like stock market prices, right? It's probably not true that if I were to take the stock market price of a stock from like January to December, that those numbers would be like all mutually independent, because obviously the stock price is not like going like this every day. It's kind of taking smooth trends, right? So the measurement at time 2 is probably related in some sense to the measurement at time 1, right? But if you're kind of like taking, random samples of like, okay, if I'm going to, look at the second hand of my watch, and I do that every once in a while, that's probably IID because there's no connection between those measurements, right? And a lot of times we're talking about, data points that have been kind of like, sampled from some underlying data in a way that's meant to be independent. Okay, so we're going to assume everything is independent, otherwise life is very complicated. So the first thing we have to do is write down the joint distribution of these data points according to our model, right? So if things are Gaussian, that's like saying the PDF evaluated at this set of data, right? So here again, this is like I have n measurements of a d-dimensional vector, right? So that probability is going to look like, for each of those measurements, I have the Gaussian PDF, right? So it's going to be the product from little n equals 1 to big N of square root of 2 pi over md. This is the very same covariance matrix that we talked about before. And this is the Gaussian function. Okay, so how do I find the best parameters, right? So kind of what I want to do is I want to maximize this number, right? I want to maximize the probability of that, or again, I just said that that's not actually a probability, but it's kind of like in the local neighborhood of this number, I want to make that as big as possible, saying that this is a likely observation to have gotten, right? Now, taking the derivative of this and say it equals 0 is a little bit of a pain, right? Because of this exponential and all this junk, right? So one thing that we often do in practice is take what's called the log likelihood, right? So we often are able to simplify things by taking what's called the log likelihood. And usually in engineering, when I say taking the log, we mean log base e, right? Not log base 10. And the reason is that we care about what values of x, maximize this function. And the reason we can do this is that, f of x, some function, and log f of x have the same, maximizers and minimizers. Again, for you mathy people, it's like saying that log is a monotonic function, so that means that a minimizer of f of x will also be a minimizer of log f of x, right? So I can kind of say if I'm looking for the places where the thing happens, then it's okay to also look at the log of this function. So what is the log of this function? Well, that's a little bit easier to write, right? So the log of this function, blah, blah, blah. Well, in log world, multiplying things together becomes adding things together, right? So this product becomes a sum. The log of this thing is whatever. Log of, and I don't really actually care about this too much, but I guess I'll write it down because I'm a completionist. Again, now this thing gets added to the log of this thing, so I get a minus 1/2 xn minus mu transpose sigma inverse xn minus mu. Okay. And so now suppose I want to find the maximum likelihood estimate of the mean, right? Mu by itself. Okay. We also want to find sigma, but let's forget about sigma for a second and just try to find the MLE of mu, right? So we want to maximize this. With respect to mu and sigma, okay? So how do we maximize? We take the derivative, we set it equals 0, right? So d mu of this, now life is a little bit more pleasant because, the derivative here, so if I take d mu and set it equal to 0, what does that mean? Well, the first term doesn't have anything to do with mu, so that just goes away entirely, right? The next part is basically saying, well, this is very much like the x transpose ax that I talked about at the beginning of lecture, right? So the sum from n equals 1 to n here of, what's the derivative? Well, the 1/2 is going to go away, and I'm just going to get sigma inverse x minus mu, or xn minus mu. I guess these should be n up here, right? So this is the same thing as saying, taking the derivative with respect to the mean and saying it equals 0. A little bit confusing because this sigma is standing for sum and the other sigma is standing for the covariance matrix, but hopefully you kind of get the gist. So now I can pull this sigma out because it doesn't depend on n, and then I can kind of say I've got this is the sum of xn, and then here, since this mu is basically just, again, being multiplied together n times, I have n mu equals 0. Since this thing here has to be a matrix I can take the inverse of, that means that basically it has a full set of eigenvectors and eigenvalues. So the only way I can get 0, the only way I can get a times something equals 0 is if this thing itself equals 0, right? So now I move some stuff around, and I move the n mu over, and I find out that my maximum likelihood estimate of mu is 1 over n. I'm sorry, I guess it should be like capital N. 1 over capital N of the sum. And so this is a pretty, reasonable result. This is like saying, if I want to estimate the mean of a distribution, what I should do is just take the average of all the values I saw, right? And that's a good measurement of what the mean is, okay? And one nice thing about this mean is that if I take the expected, so I can think about this as some random number that depends on the data that I saw, right? And so one nice thing is that if I look at the expected value of this mean, what I get is 1 over n times the expected value of each of these guys. Since everything is IID, all these expected values are going to be the same. So this is actually like, telling me that when I do this process, the expected value of this random thing that I've produced actually should be the expected value of x, right? So the estimate works in a way that makes sense. Okay. Any comments? Yes? So basically, this here is kind of like a 1/2, remember that we had something like this from before, right? The derivative of this with respect to w is, this part is going to be basically 2aw, and then this 2 goes away. So basically, I'm just going to get this part is where the derivative is. Other comments or questions? So I'm pretty sure that if you took a probability class, that at some point you talked about estimation, and I think that you probably saw at least in one dimension, like how do I find the maximum likely estimate of the mean of a Gaussian distribution, right? That's like the most simple problem that you can do in estimation, right? Things are a little more complicated when I'm trying to find the maximum likelihood estimate of the sigma, right? The sigma is a matrix, and also the sigma itself has some properties, like I know that I have to be able to get a symmetric matrix at the end. So instead of deriving that in class, I'm going to cut to the chase and say that, we can show the professor's refuge. We can show that the maximum likely estimate of the covariance matrix is, again, kind of the thing that you would expect. Kind of what I do to form this covariance matrix estimate is to take all my data points, I've already estimated the mean, and I form up basically the sum of these n matrices, okay? So the bad news is, so this basically, is kind of, this property up here with the mean was called unbiased estimation, right? Unfortunately, this is a biased estimate, meaning that if I were to take the expected value of this thing, I wouldn't get back exactly the true sigma. To make it an unbiased estimate, what I would need to do would be to kind of take 1 over n minus 1 times this sum is unbiased. But I can't have both unbiased and maximum likelihood at the same time, right? So again, if you're interested in this kind of thing, taking a course like detection and estimation or stochastic signals and systems are both places to learn more about this issue of biased and unbiased. I'm not going to make a big deal of it in this class so much, but it is a good thing to know about, right? So the first problem on the homework number 2 is basically, I give you some data, use these equations to fit a Gaussian to it, right? I don't want you to use some sort of Python package that says, fit dist, x, right, with Gaussian. You could just write this down yourself in 2 lines of Python code, right? So, and again, you can kind of verify that it works with some 1D data, which I think is actually all I'm asking you to do on the homework. But then in theory, it should work for any dimensionality of data. In fact, I'm trying to remember, actually, I think the homework is a 10-dimensional data set or something like that. So I think that actually you do have to write a fully general Gaussian, maximum likely estimate, but you can test your function on 1D or 2D to make sure it makes sense first, right? That's always a good thing to do. Okay, questions or comments? Yes? So biased estimate means that when I take the expected value of my estimate, I get what the truth should be, right? Which is kind of like what I want, right? Here, if I took the expected value of this, just as a side note, so it turns out that, if I took the expected value of this sigma and worked through all the math, what I would get would be, n minus 1 over n times the, sigma true, right? What that means is it's a biased estimate, because if I want it to be unbiased, I should get this exact thing, but instead I get something that's a little bit off, right? So just as a side note, if you ever, you all probably still have a graphics calculator somewhere in your closet, right? So if you ever look at your calculator, sometimes when you're computing the sigma for a set of data that you punch into your calculator, you have an option for computing 1 over n, like the average of the sigmas, like the average, or there's also a button that says like 1 over n minus 1. The reason that 1 over n minus 1 button is there is in case you want the unbiased estimate, right? So if you're a statistician, you care about that kind of thing, okay?
So might we end up having bias or
Well, I mean, the scenarios don't come from the data. It comes from the nature of the PDF, right? So like when you work through the math to compute the maximum likelihood estimate, then a natural next question is that estimate biased or not, right? Or if I took the estimate from somewhere else, right? So I mean, not every way of estimating these numbers needs to come from this process of taking the derivative and say equals 0. I could have some heuristic or something like that, right? But then I could ask, is my heuristic biased or not, right? So it has to come from the underlying PDF and the nature of how you get the estimate. It doesn't have anything to do with the data set itself, right? Or the situation where I got the data from. So for example, I could ask you on a homework or on an exam, here's some data, fit me an exponential distribution, right? So then you have to take the derivative with respect to that one exponential parameter lambda, and then I could ask you, is that estimate biased or not, for example, right? Okay. So questions or comments so far? So I would like to think that everything that I've said so far, except for perhaps the biased, unbiased part, is something that you should have seen in probability class before you got to me, right? So I took a whirlwind tour. Like normally to get to estimation theory, I would take 10 weeks of a class to derive what a PDF is and do expected value and so on, right? So I gave you kind of like the 20-minute version of the first 10 weeks of a probability class, right? Of course, there's a lot more to say about probability, and we will say more about things like, I didn't talk about conditional probability or Bayes' theorem or anything like that, but there's definitely more probability than what I said here, but this is the key point for today, okay? So if any of this seemed a little bit like what, then certainly go back and take a look at a probability textbook. Also, I have all these probability videos online, so if you took an RPI class, you may have already seen my probability bites videos, which are good ways of saying like, okay, what is conditional probability again? Then there's an 8-minute video that you can watch to watch that. So that's a good place to go back if you're ever like kind of confused about things. Okay, so now let me tell you some stuff that I don't think that you ever learned in probability, right? So certainly the Gaussian is the most common way of fitting a distribution to some data, right? But in the real world, it's not typical that your data is Gaussian. Like if everything was Gaussian, we would hardly need any machine learning at all, right? But in practice, the data that you get is weird, and it's got like patches of ups and downs, right? So for example, if I had a distribution like this is not like a good fit to a Gaussian, because if I fit a Gaussian to it, I would probably get something like this, which is not horrible, but also clearly it's not doing a good job of modeling all the stuff that's happening at the high end, right? So kind of what I want is there a better way to get a density estimate of the actual data, right? And so that's what we're going to talk about next, and that's called non-parametric density estimation. Before I go there, one thing that's kind of like a halfway mark is, well, maybe I don't necessarily need to go all the way to just like some arbitrary function. A very common model is also called mixture of Gaussians, right? We're going to talk more about that on Monday, but another model for your data could be what's called a mixture of Gaussians. Or you may see it like MOG. What that's saying is that the PDF at X is the sum of a bunch of kind of sub-Gaussians. Right? So this is kind of like saying, this is a Gaussian with mean mu m and covariance sigma m, and these pi's are basically like what you'd call mixing weights or mixing coefficients. And these add up to 1. Right? So one way of thinking about this is like saying, okay, I've got some data, and it's like 2/3 of a Gaussian over here plus 1/3 of a Gaussian over here, right? So you could get, at least in 1D, a distribution that might look something like this, right? And this thing is actually made up of the sum of a Gaussian like this, and a Gaussian like this, and a Gaussian like this, right? So it's like saying each of these Gaussians is kind of weighted by how much contribution they have to the density, and then I add those things up to get the full PDF, right? So for example, I'm trying to think of some sort of like off-the-cuff mixture of Gaussians things. Like say, okay, suppose there are like, two different populations of people. People who drive like super efficient electric cars and people who drive like huge gas guzzling cars, right? So the mileage per gallon of these cars over the whole population could be like, say, okay, well, 60% of the people drive the gas guzzlers and 40% drive the electric cars, and my MPG overall is going to be like a Gaussian over here plus a Gaussian over here, weighted by the populations in each of those places, right? So like definitely in a computer vision problem I'm solving right now with one of my students, we're fitting these mixture of Gaussian models to some data that we have because, it is a little more complicated because now I have to estimate for each Gaussian the mean and the sigma, and I also have to estimate these m numbers that tell what's the proportion of each of these Gaussians. And we're going to talk about that problem exactly next time. So we basically fit this to data with what's called the EM algorithm, which stands for expectation maximization. And so we're going to talk about that algorithm next time. So that's a way, it's still a parametric model, right? Parametrized by the means, the sigmas, and the weights. But it's a little more complicated. And there is no like single closed form answer, right? So when I do a, equation like this, or like this, I can write down the answer immediately from looking at the data and just doing a computation on the right-hand side. In practice, I typically have to do some sort of like iterative numerical process to get to good values of these weights. And that's the other thing we're going to talk about next week kind of is, how do I, solve these kinds of problems numerically, right? We're going to talk about an algorithm called gradient descent, which is like the workhorse of machine learning. That's also coming next week. Okay, so let's talk about now switching gears to, say I had some really weird data set that was not well modeled by a mixture of Gaussians at all, right? So I could have some data that looked like, some sort of wackadoodle data, like an exponential thing, and well, no, that's not good. Can't do that. It's not that crazy. So like maybe I have data that looks like, this, and then I got, something that looks like this, and then I've got something that looks like this, right? This would be a bad idea to try to fit like Gaussians to because it clearly doesn't look like a bunch of symmetric peaks, right? But still, I should be able to talk about like how can I, model this data? How can I sample from this data to draw from this distribution to get something that looks similar to the data that I saw when I trained my algorithm, right? So, we can fit data in general, with what's called non-parametric density estimation. Meaning that the data is not, or meaning that the model for the PDF is not just described by a few parameters. In practice, what it means is that I'm kind of using the data points themselves to generate this PDF in ways that I'll show you in the next couple of minutes. So, for example, the easiest thing to do, focusing on just one-dimensional data, is the histogram, right? So the starting with 1D. This is probably the way that you would think about following your nose, the easiest thing to do. Right? Basically, what I would do is I would form kind of like this frequency distribution of, if my little hash marks on this x-axis were where I saw data points, what I would do is I would form up some bins, right? So I kind of draw evenly spaced bins along the x-axis. And then I would count, how many data points there are in each bin. And that would be kind of like a very crude model of my data, right? So basically, this is like saying, I have, bins of width delta, and then inside each bin, I count the, number of data points in the ith bin. Call that ni, right? So again, if I'm just counting these numbers, this thing is not actually going to be a true PDF in the sense that, if I add up all these numbers, what I'm going to get is capital N, the number of things, and also I have to think about how wide the bins are. So I kind of need to scale or normalize this histogram to make like a true PDF. So to create a valid PDF, and again, this is slight abusive notation because it's like a PMF actually. What I could do is I could say the probability is the fraction of points lying in that bin divided by delta, right? This is basically going to be a piecewise PDF satisfying this integral equals 1. Right? So let's switch over to some examples and see how this works. So look at my notebook. All right, so first what I'm going to do is I'm going to make some data, right? So what I might do, for example, is, and I'm sorry, I need to actually think about my Jupyter Notebook font. I wonder if there's a way to do this. Of course, I should have done this before I got here. Theme, language, increase terminal font size. I said increase. Did it take any effect? It's unclear. All right, well, whatever. So I'll work on this before next class. So let's take some data. And what I can do, for example, is I can say, OK, let's make a vector that contains 200 points. So I'm going to take a rand n is what I can use in MATLAB to make Gaussian distributed data. I'm going to say, give me 200 data points, a 200 by 1 vector. And I want the, I'm going to multiply this by 3, and I'm going to shift it over by 2. That means I'm going to make basically a mean is going to be -2, and the standard deviation is going to be 3, right? So I'm going to kind of shift this vector over, and then I'm going to make some more data that, has 100 samples from a distribution that is located at +3. So if I was thinking about this like a Gaussian mixture model, this would be like basically saying the mixing coefficients are 2 to 1, right? So I've got twice as much data in the first Gaussian as I do in the second Gaussian. So in theory, I should be able to find that the pi1 is 2/3 and the pi2 is 1/3. But I'm not doing that. All I want to do is I want to just look at the data. So let me look at the data as a histogram. So, I mean, here is an example. You can kind of see that there is like a kind of a peak around, where did I put it? I put it at -2, and there's kind of a peak around +3, right? But, as with everything, there is a choice about how wide I make my bins, right? So here, MATLAB's default made me 9 histogram bins, right? But to make a density estimate, I have a choice about how wide I want the bins to be, right? So I could say, give me bins that were smaller, right? So these bins look like they're about 2 units wide, right? So if I said instead, give me bins that were 0.5 units wide, then I would get a histogram estimate that would look like this. And here you can kind of see a little bit more these kind of 2 peaks, but still kind of, so one thing to observe is that, this is somewhat higher resolution, but it's also become kind of noisier, right? Because it is random where I got these samples from. If I make the bin width even smaller, like 0.1, then basically only a few samples are falling in each bin, and it looks really choppy and kind of maybe not as useful to me, right? So this is kind of like the first lesson of density estimation, is that choosing your delta is important, right? And so the other thing to observe is that this is the true literal histogram, right? Counts of how many things are happening. MATLAB does provide me with a option to normalize this. If I say normalization PDF, then I get the same graph, but the heights of the bars basically give me something that's a valid PDF. Like if I were to multiply the areas of all these boxes together, I would get 1, and I could say, okay, now this is a true PDF if I wanted to use it to operate on something else, right? So that's like the most simple density estimate that we could make, right? But let me just write down what did we note, right? So kind of problems with this are that, if my delta is too small, if my bin width is too small, and I guess, yeah, I said that. So if my bin width is too small, then I get like, kind of spiky structure, lots of kind of stuff not in the underlying true PDF. Right? So, if I look at the picture again, like, yes, I kind of still see the 2 peaks, but I also see a lot of other spiky stuff that doesn't really help me appreciate that these are kind of innate Gaussians, right? Again, part of this also depends on how much data I have, right? The fewer data points I have, the more, spiky and random my output is going to be, right? If I had 2,000 data points in one place and 1,000 in the other one, then I'd probably get a much smoother looking thing if I took my bins to be big enough. And of course, in the limit, if I took millions of points, then the histogram would converge to the PDF, but I don't always have the luxury of taking millions of points, okay? So that's one issue. The other issue is that, if sigma is too big, then the PDF that I get can be too smooth, and I won't capture multiple, what you call multiple modes, right? What I mean by that is that, if I were to, say, give me bins that were like, 4 wide, then I don't really even appreciate that there are 2 separate peaks in this distribution, right? So it's always the secret, it's like the secret knob of like, what is the right number to give me a good density estimate? And there really is no like right answer. There are definitely some heuristics and rules of thumb, but in practice, you have to kind of like feel around to make sure you're happy. But there are better ways to do it, which I'm going to tell you about in a second, that you wouldn't just use the histogram, okay? Like one thing that's definitely a problem with this is that no matter what you do, your histogram is taking a discrete hop, a jump between adjacent bins, right? So the sensitivity of the bins to the grid that I use is going to make this kind of an inconsistent estimate, right? So suppose that there were some data points like right on this area. If I were to just shift my, bin edges a little bit left or right, I would get a totally different looking histogram, right? And so in general, this type of approach is generally sensitive to bin edges. And finally, this is a case, I think I mentioned this last time, that, the other problem with this kind of approach is the curse of dimensionality. Woo. Right? I'm only showing you this in 1D, right? But in the homework, I'm asking you to deal with like 10-dimensional data, right? So if I asked you to take, 10-dimensional data and grid it up just with like 10 bins on a side in 10 dimensions, that's already 10 to the 10th bins, right? Billions of bins. And so you can imagine if I had data, unless I had like trillions of data points, I'd really only be likely to get like 1 point per bin, right? So I'd be really hard pressed to get a good density estimate by trying to slice up the probability space into an even number of bins if my dimensionality was even a little bit higher than 2 or 3, right? So that's a good reason not to do this in general, is that maybe it will work in 1D, but it won't work in 10D, and God forbid that you have 1,000 features, you're never going to be able to have enough data in any particular bin, right? So we kind of want to get away from using these fixed bins. But there are some things that we want to take away from this idea, right? So there's some notion that I should build my PDF kind of based on what's going on in my local neighborhood, right? So if I'm in a neighborhood where I have lots of points that I got from my data, then the PDF should be higher over there. And if there's nothing happening in some region of the data space, then the PDF should be low over there, right? So there is some notion of points and neighborhoods that we want to preserve from this kind of initial stab at things, right? And so the first thing I want to tell you about, which is very common, is what's called kernel density estimation, okay? Also known as Parson windows. So a better approach is what's called kernel density estimation. Sometimes you see this called KDE, also known as Parson windows. I'm always jealous of these guys who get their names on things. Like there's no Radke windows. There are never going to be any Radke windows. I'm just too old. All right, so the basic idea is the following, right? So kind of what we're going to do, and it's a super simple idea, right? And I guess I can tell you the idea first, but what we're going to do is to make a PDF, right? So let me just actually say the idea first, and then I'll go into the math, right? So the idea is that, again, if I imagine that I see a bunch of data points, what I'm going to do is I'm going to build a little mini PDF around each of these data points and add them all up, right? So for example, what I could do is I could say, okay, around each of these data points, I'm going to build a little density. And then when I add all these things up, what I get is something that looks kind of like, well, I guess it kind of looks like this, but basically the little Gaussians or densities that are close to each other are going to build up to kind of look like a larger local probability, right? So this is the idea, is we're going to build little PDFs on top of each of our existing data points, okay? So here's the kind of, backing up, and let's talk about it from first principles, right? So the basic idea is, let's consider, and this is going to be like full, like arbitrary dimensional space, right? Not just one dimensional. So let's think about a region R. So the probability that my sample falls within that region is basically given by integrating over that region the PDF. Okay? Let's call that P. Now let's suppose that I have n data points, right? This is my sample, my observations, right? So now let's say we have n data points. How many of those data points do I expect are going to be inside R, right? Well, if you remember probability, you should think about this as kind of like a coin flip, where basically success is that the sample lands in R, failure is the sample is outside R. And since every sample is assumed to be independent, I basically got the sum of a bunch of coin flips, right? Which should be familiar to you as a binomial distribution, right? So basically the expected number of points in R, let's call that K, is equal to basically, because it's a binomial, it's like saying I take the number of data points I have times P, right? This is the expected value of the binomial. Again, if that seems a little bit like distant memory, then that's another thing to kind of go back and look in your probability notes about, right? It's like saying how many successes out of n trials. That's a binomial random variable, right? And the expected value is basically n times the number of trials times the probability of success, okay? Okay, so basically what I'm trying to do is I'm trying to build something out of a bunch of these numbers. K is the number of points inside the region, n is the total number of points, P is the probability of success being in the region, right? And now what I'm going to do is I'm going to say, okay, if I were to make those regions small, the smaller the region is, the more I can model the region as being basically a flat probability, right? So maybe at the macro level, the PDF is bumping all around, but if I were to turn my microscope down and just look at some local thing, well, the PDF is going to be locally, pretty much the same value if I turn my resolution of my microscope down enough, right? So if the region is small and has volume V, we can model the probability as roughly constant, right? That's like saying that, this P value that I have is basically like, taking P of X times V for any point X in the space. So kind of putting it together, what this is saying is that what I'm going to do is I'm going to build some regions, and I'm going to build a probability estimate based on a bunch of numbers, right? How big the region is, which is its volume, how many points I have, how many points fall in the region, and so on, right? Because really what I want to do is I want to estimate this number here. So if I kind of rearrange all this stuff together, what I get is the following. So putting it together, what I have is the density estimate at X is basically, K over NV, right? So the idea is that I'm going to build density estimates based on little regions that have volume V, and then I'm going to look at how many of the points fall inside those little regions over the total number of points, okay? And so this is, actually not that different if you look back at what we did with the histogram, right? The equation here is very much like this equation, right? Because here, the volume of the bins in 1D is delta, the width of the bins. This is the number of things falling in each bin. This is like the number of points I have. So it's really not that different than what we already talked about with the histogram, right? The tricky part is that we're going to not just have these fixed size regions. We're going to kind of have the regions depend on the data a little bit. And it's also a little bit like simultaneously contradictory, right? Because to make this work, so this is tricky, let's just say, ... We basically need both, R and V to be small to kind of satisfy this assumption that the probability is roughly constant. But I also need there to be enough points that are going to fall into the bin to make enough of a density estimate, right? But we also need, K to be large. So kind of balancing the number of points that fall into the region and V is the issue, right? So technically, again, I'm not going to make this a super theoretical lecture any more than it is. Technically, the rules that we need to make this work at all are that, formally, what we need is that the more points I have, like the regions get smaller and smaller, but kind of contradictory is that the number of points in each region gets bigger and bigger, and also that the, each region makes up kind of only a small amount of the probability, right? So all these things happening at once, there are ways of setting this up to make it happen, but it's a little bit confusing. Again, if you're not really clear on this, don't worry about it too much. And this is the reason that you have a textbook as a accompaniment to my lectures, is to go back and read about Parson windows to get all the fine points, right? I'm going to show you some examples, right? But I think that to really understand it, this relationship between K and V requires a little bit of like offline thinking than just hearing it from me once in class, okay? So basically, Parson windows are a way of fixing V and determining K from the data, okay? So here's how Parson windows actually kind of operationally work. So one idea is to, take a unit cube, like a unit d-dimensional cube, centered at the origin, right? That's like saying, in 1D, that looks like this interval. In 2D, it looks like this box, right? In 3D, it looks like a little cube. All these cubes have one unit on a side, right? And so this we're going to call K. And it equals 1 when the absolute value of each dimension is less than a half for all dimensions, and it's equal to 0 otherwise, right? So that's kind of like the formal definition of this cube, okay? And then I can use, and this is called a kernel, right? So I'm going to call this a kernel. And we're going to come back to kernels in other parts of machine learning. It's basically, one way to think about this is like a little PDF, right? Because the integral over this cube is equal to 1, right? And so now, if I think about kind of transforming this kernel, then what I could do is to say that this kernel here, what does this mean? This is like a box now that is, first of all, I've moved it, so it's centered around each of the data points, right? So this is basically like one of the data points. And this H is what we call the bandwidth. And so this is basically just something that is 1 inside a cube of side H centered at point little xi, or xn, sorry. At 0 outside of that. So it's like I'm basically scaling and shifting this little box to be on top of each of the data points. And so now these little cubes are basically my collection regions, right? So I'm basically specifying the volume of this cube, and I'm going to ask, okay, for each of these places, how many data points are falling inside this box, right? So now I'm going to turn this into K is equal to this. This is basically the number of data points inside the cube of edge H, at each xi, or at each xn, and I'm adding them up, right? So my overall density estimate is like saying, okay, add up all of these little k's, right? So here, my overall density estimate is saying I take the average of this thing like so. Right? So here, this is like saying this is playing the role of the volume, right? Because the volume of this cube is basically the edge length to the d power, how many dimensions I have. This is playing the role of k, right? Which is how many points fall inside the cube. And so this is just nothing more than the same k over nv I had from my kind of bigger picture. And I'm kind of fixing v by saying I want to have regions that are this big, and then I'm asking you to tell me what k is for your data, right? And so this is basically like building a PDF up out of little cubes that are centered around each data point. So it's basically like, building a PDF out of little cubes at each point. And so let me actually show you this over here in MATLAB. So for this, I'm going to actually just use a smaller number of points to make it clear where the samples are. And again, this is something that I want you to write yourself. I wrote a little function called kernel density estimate illustration where I'm saying, okay, let me take these boxes, and let's suppose that I use boxes of side 1, right? So kind of here what you see is that the red dots on the x-axis are where those points were sampled. And those little blue dotted lines are little boxes that I'm putting around each data point. And when I add up all those blue dotted lines, I get the black line, which is the overall density estimate, which you can see kind of looks like the same two-peaked thing that I know is driving the generation of this data, right? Again, I have the same problem I had before with choosing how big my little boxes should be, right? So if I said, okay, I want these little boxes to be like 2 units wide instead of 1 unit wide, then I would get a smoother density estimate, right? So here again, things are still a bit spiky because I'm basically adding up these sharp-edged boxes, but I'm seeing this. And of course, if I went too far in either direction, right? So if I went to say, okay, I want to have these boxes be like edge 6, these boxes are too broad, right? These boxes are drowning out the fact that there are 2 different modes. And conversely, if I made the boxes like super small, then my density estimate would be like super choppy, right? So part of the problem here is that, well, so you may ask, well, why boxes? The picture I drew to motivate this was like little Gaussians, right? So I can use any valid PDF I want for the kernel, right? And in practice, when you do powers in Windows, you're typically using like a little Gaussian kernel, right? So that makes life a little bit easier, right? So in practice, we don't use kind of like hard-edged boxes, but instead use Gaussian kernels. Right? So that's like saying that my density estimate is the sum of a bunch of Gaussian kernels. And again, let me just say this, I'm going to just say to make this easier, this is in 1D to make it cleaner to write. So it's like saying I'm going to add up a bunch of Gaussian densities where, well, I guess I can write it like this. Right, this is like saying, the mean of each of these Gaussians is at the sample point, and I have to then, again, specify kind of like this sigma, which is kind of like playing the role of the bandwidth from before, right? So this is like saying, okay, if I go back to my picture, I can now ask for a Gaussian window. And if I say I want a unit variance Gaussian, then here you can see now around each of these points I've drawn a little blue Gaussian, and those blue Gaussians add up to something that is not that bad compared to the true underlying density, right? I see these 2 peaks. Maybe I know that there's more data on the left than the right, so maybe I want the peaks to be different. But again, this is just a small random sample of data. And I have the same problem, right? If I make the variance of the underlying Gaussians too big, then I just get basically like one big smooth PDF, right? Not a very good estimate. And conversely, if I make the Gaussian window too small, then I get a really kind of spiky estimate that looks like a bunch of little tightly, tight Gaussians around each point, right? So there's, again, a trade-off of how big should my bandwidth be, right? Same kind of deal. So let me just kind of restate what I wrote down here, which is that, the sigma too big means that I have, density is too smooth. sigma too small means I have many tiny sharp peaks. So what I want you to do on the homework basically is to play with the data that I give you. I think I'm basically just telling you what I want your bandwidth to be, but I asked you to do it in very high dimensional space, right? So it's very hard for you to reason about whether or not your answer is correct without doing a little bit of debugging first on low dimensional data, right? And I'm not asking you for your debugging results because you're gonna have to kind of do that on your own and convince yourself you've got the right density estimate. Now, like I said, I don't want you to use built-in kernel density estimators from some Python library. I want you to write this yourself, and it's not that hard to do, right? It's just this function, right? If you want to output the density at x, you just sum up a bunch of Gaussian values. It's like one line of Python, right? So for I equals 1 to n, this number, right? So I don't want you to go right to a library to solve this problem that you should be able to solve yourself. And the function is even easier to write for boxes, which I'm also asking, right? Because then it's just basically like a, am I in range of this point or not? Yes or no? And adding a bunch of like ones and zeros, right? So you guys should be able to handle that. Okay, so let me stop asking. Questions or concepts about the general concept. I need to do one more thing before I let you go today, so I don't want to get down to the weeds too much, but basic questions. Okay, the last thing I want to talk about is something that is an alternative. So basically what we're doing in parse windows is we are specifying the V, the volume, and then we're counting the number of things that fall into that volume, right? Another way of thinking about this is to say what's called a k nearest neighbor estimate, where it's like saying, okay, I'm not going to specify the volume, instead I'm going to specify the k, the number of neighbors, and I'm going to let the volume grow until it encompasses that number of neighbors, right? So, there's also something called what's called k nearest neighbor density estimation. Right? And the idea is to fix k and let v grow to include k points. Right? So it's kind of like saying, I take a point that I care about. I want to know what's the density estimate at this point. I basically say, okay, suppose that, here's my actual data points, right? And now suppose I want to have like, k equals 3. What I do is I kind of expand my radius here. So now I've got 1 point, now I've captured 2 points, and maybe here, these are pretty crappy circles, but you get the idea. Here I've captured exactly 3 points, and I stop my circle at this point. So then I can say, I measure the V here at this point, and my density estimate is basically still like the same kind of like K over NV, right? So basically the idea is that I just want to see what I said in my PDF for a second here. I know I'm running out of time, but I want to be careful. And of course, I don't have the homework right in front of me. Right. So basically here, the density estimate at x is k minus 1 over nv. The reason that I have a minus 1 here has to do, again, it's a statistical thing that has to do with the fact that I'm growing the bubble just until it hits the kth closest point, right? So in some sense, what I care about is, going right up to that edge, right up to that closest point. So the question is like, okay, so if you're actually going to do this, expand, the bubble until it hits these k points, k you've fixed, and you know how many points you have. What is v? So for v, you have to think about like what is the volume of a ball in n-dimensional space that has a certain radius, right? So let me just write that down for you. So what's the volume of a sphere in d dimensions, we need that for the numerator, or the denominator, sorry. All right, well, what's the area of a circle? Nobody? Pi r squared. What's the volume of a sphere? All right, what about 4 dimensions? No one knows, right? So, yes, we know that in 1D, it's basically going to be like 2r. In 2D, it's pi r squared. In 3D, it's 4/3 pi r cubed. What's the pattern, right? Well, it's clear there's an r to that power. There's a pi involved. Turns out that the volume of a d-dimensional sphere with radius r is pi to the d over 2 over the gamma function so you're going to need this for the homework. So basically here, what is this thing? This is called the gamma function. So basically the gamma function is like the factorial function, actually. You already know the factorial function, right? If I have to evaluate this with a fraction, basically it's like the same thing, right? It's like gamma, it's like saying I take, n minus 1/2 times n minus 3/2, dot, 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 all the way down to 1/2, and then I multiply that by the square root of pi for some reason, right? So this is like a new function for you. Don't worry about this because it's built into MATLAB and Python, right? So if you just say gamma of this number, you're going to get the right thing. And it turns out that this kind of accounts for the fact that there's a pi here and a pi here, but in 4D, the actual answer is pi squared over 2r to the 4th, apparently, right? So amaze your friends with this new knowledge that you've acquired today about the volume of an n-dimensional sphere, right? So, but basically this is all you have to do, right? Is that you basically, if I ask you for the density estimate at a given point, you expand your radius until you hit the number of points I ask for, and then you divide by the area of the sphere, right? So the way that this density estimate works is a little bit wonky in the sense that, and I know we are a little bit over time, I'm going to finish up right now. So I also wrote basically a KNN illustration of taking, say, say I want to evaluate this density between minus 6 and 6, and I take my data points and I take 5, nearest neighbors. Maybe I'll use some operator. What didn't you like about this? Oh, I see. Right, so this is a density estimate that, again, it still has the same kind of characteristic 2 peaks, but it's a little bit weird and spiky. And part of the problem with this density estimator in general is that it doesn't actually produce a valid PDF like this. If you were to integrate this, doesn't integrate to 1. So I'm not trying to tell you that k-nearest neighbor density estimation is the way to solve this kind of problem. I'm just trying to tell you that's a different way of doing it. And we will come back to k-nearest neighbors as a means of classification, which is like a super useful way of classifying points. So that's why I wanted to kind of mention it here. But I think in practice, if you're going to do non-parametric density estimation, the natural thing to do would be parsed windows. And that's mainly what you're doing on homework too. OK, so since we're a little bit over time, I'm going to stop now. And I'll take questions up at the podium at the end. So have a good weekend. Enjoy the carnival. And I'll see you on Monday.